Henri Darmon from McGill University to give his lecture on rigid analytic modular symbols. Thank you, Henri.
Thank you, John, and thank you to the organizers for inviting me to speak here. It's a great, sorry, well, that's strange. I'm having some trouble with my, okay, now it's working. Yeah. Okay, so it's a great pleasure to give this lecture here. It's a great honor as well to participate in this event in memory of Peter Swinnerton-Dyer. Now, of course, Barry's lecture reminded us of the tremendous influence that Peter has had on our subject. And we hardly needed to be reminded of that, of course. I mean, one of the most celebrated conjectures in mathematics bears his name. And also something that Barry mentioned as well in his lecture is one thing that impresses me a lot about Swinnerton-Dyer is also his mathematical style. I mean, he was one of the earliest and very successful proponents of the idea of number theory as an experimental science in which one uses computers and experiments to arrive at conjectures and eventually theorems. And that's certainly a style, an approach to the subject that was far less common in those days than it is now. Of course, now it's much more widely practiced now that computers have become much more sophisticated and powerful. And so, I mean, that's certainly something where Swinnerton-Dyer was a pioneer. So I thought I'd give a lecture that with a sort of a computational emphasis, which is also what corresponds very much to my own mathematical tastes. And thinking back on the contributions of Swinnerton-Dyer, I was thinking about those that were particularly influential to me, and my thought immediately turned to this fantastic article with Barry Mazur entitled "The Arithmetic of A Curves," which was published in 1974 in Invenciones. And this is an article that develops many themes that have been extremely influential later in the subject. It's actually divided into two parts. So the first part explores an intriguing and still somewhat poorly understood to this day construction of rational points on elliptic curves via so-called inflection points arising from modular parameterizations. And then the second part of the article introduces the Mazur's, what's now known as the Mazur-Swinnerton-Dyer P-adic L function of an elliptic curve, constructed via modular symbols and the formula of Birch-Manin, which Mazur also recalled in his lecture. And it formulates an Iwasawa main conjecture in the setting of elliptic curves. So that, of course, has led to a tremendous amount of mathematics in the ensuing decades. So this article, when I read it in the late 80s, I guess, when I was a graduate student at Harvard, made a tremendous impression on me. And I want to talk about some of the things I did later that were sort of strongly influenced by the reading of this paper. So I'm going to begin by talking about modular symbols, which was also a key object in Barry's lecture right before mine. I'm going to take a slightly different approach to it. I mean, maybe my definitions differ a little bit from those that Barry introduced. So for me, a modular symbol is attached to a module M endowed with an action of the group SL2Q of 2x2 matrices with rational entries. And then an M-valued modular symbol is simply a function defined on pairs of endpoints on the projective line over Q with values in M. And the only requirement that one makes in my notion of modular symbol, which is a bit different from Barry's, is that this function be additive in the endpoints. So IRS plus IST should be IRT for all triples of points in P1 of Q. So this is the kind of thing that you would get formally if you had some differential and you were defining a function by integration from one point to another. And now this set of modular symbols is naturally a group, of course, under addition. And it's endowed with a natural action of the group SL2Q by left translation. So the modular symbol gamma I is defined by this formula. Okay, so I'm going to denote by MS of M the group of SL2Q, it's the SL2Q module, in fact, of M-valued modular symbols. Now, the key reason why we're interested in these objects, why they're useful in the study of modular forms, is that they're intimately connected to modular forms. So for example, maybe the most concrete and basic example of interest is in the setting of modular forms of weight 2, say on some congruence group, like the Hecke congruence group gamma naught of n of level n. So if we have if we give ourselves a cuspidal new form of that level, then there are two periods, the so-called real and imaginary periods attached to the cuspidal new form, which are uniquely characterized by the property that if I look at these integrals, so I think of the f of z dz as being an invariant differential on the upper half plane, invariant under the action of the Hecke group, and I take the integral from R to S. Now the cuspidality of f implies that this integral converges, even though R and S lie on the boundary of the upper half plane. Of course, one has to define the integral appropriately. One has to integrate along with the geodesic, the hyperbolic geodesic, joining these two endpoints. So that gives us some kind of real number here. I've taken the real part of this integral. And the content of what I said before is that after dividing by this period, one gets something which is actually z valued. So they're all integer multiples of a common period, and likewise with the imaginary parts. I guess here I made a bit of a small mistake. I shouldn't have said that omega f is an IR, given that here I already took the imaginary part. Okay, so the point is that these two functions belong to this group of gamma naught of n invariant modular symbols with values in z. And there are many applications of the notion of modular symbols. It's a fantastic notion, very concrete and very powerful at the same time. So, for example, it underlies the construction of the Mazur-Swinnerton-Dyer P-adic L function attached to an elliptic curve, say, if f has rational coefficients, as I assume here. And it also allows the explicit calculation of modular forms of given levels. It's what led, for example, to the fantastic Cremona tables, which tabulate all elliptic curves and maybe now all modular forms up to given levels, and the database in LFMDB as well. So basically one can consider this group of z-valued modular symbols or q-valued modular symbols and diagonalize this group after tensor with C or R as a module over the Hecke operators. And then each line determines a system of Hecke eigenvalues, which gives rise to modular forms. So these are the important aspects. And then, of course, we also heard in Barry's lecture that the statistics of these underlying modular symbols are also quite rich and interesting. Now, I also want to mention another approach to calculating spaces of modular forms, which is going to be crucial for what I'm going to talk about later. So there's an alternate approach, which is known sometimes as the méthode des graphes. That was, I think, the terminology introduced by Jean-François Mestre, which consists in considering functions on a certain set, namely, so this is an approach which works well for calculating modular forms of prime level L and weight 2. And so one considers the set of isomorphism classes of elliptic curves in characteristic L. And we know that that set has cardinality roughly L over 12. And so it's a finite set. And it's endowed with a natural action of Hecke correspondences. If you have a supersingular elliptic curve in characteristic L and you want to define the Hecke operator TP, you just send that to the formal sum of the P plus 1 P-isogenous elliptic curve, supersingular elliptic curves in characteristic L. And that gives rise to a collection of commuting endomorphisms on the set. And the main proposition is that the space of such C-valued functions on this set of supersingular elliptic curves is endowed with an explicit action of the Hecke operators, which factors through this algebra, which I'll call T2 of gamma naught of L, namely the ring of Hecke operators acting as endomorphisms on the space of modular forms of weight 2 and level L. Okay, so then by diagonalizing these operators, or sometimes concretely called Brandt matrices, one gets a nice concrete approach to calculating these modular forms. So if we want to compute the new forms of level L, we can do it by this approach. Now, one of the drawbacks is that one can only use this to conveniently calculate modular forms of prime level. But there are nice variants of this. So one of them is based on what I call the isogeny graph. So this set of SSL is quite rich. It's not just a finite set. It can also be viewed as the set of vertices of an infinite collection, in fact, of graphs. So if x prime p, which is different from L, then I can identify SS of L with the vertices of this graph, which I'll call G of LP. And simply, it's defined by decreeing that an ordered pair of points, namely an ordered pair of supersingular elliptic curves and characteristic L, is an edge of this graph, precisely if the two elliptic curves are related by a cyclic P isogeny. And we say that a function on the edges of this graph is a harmonic function if so here I'm thinking of this graph really as an ordered graph, even though the relation of being P isogenous is a symmetrical one. Okay, so if E1, E2 is an edge on the graph, then so is E2, E1, but I nonetheless want to treat these two edges as different edges on the ordered graph. And then I say that a function is harmonic if its value at the edge where you reverse the orientation is minus the value of at the original edge. And if the sum over all the edges which have a common source of the function at that edge is 0. So this is what such a function models what we call a conservative flow on the graph, wherever the amount of flow coming in is equal to the amount coming out, so to speak. And I'll denote by f sub har of G the space of harmonic functions on this graph, on a graph of G. Okay, and then the proposition, which is a variant of the one I had in the previous slide, is that the space of harmonic functions on the isogeny graph attached to L and P is endowed with an explicit action, faithful action of the Heck algebra of level LP. So consisting of, or rather the quotient corresponding to the operators acting on the new subspace of the space of modular forms of level LP. And so this gives us again a concrete approach to studying this space of modular forms. So I'm going to now talk about a structure which is a bit of a local variant of this isogeny graph, and it's going to be related to the universal covering space, in fact, which is based on the notion of the Brouatitz tree. So this tree is simply a graph whose vertices are in bijection with lattices, with ZP lattices in QP squared, taken up to homotopy. So it's a familiar object. And of course we say that two vertices are joined by an edge. If the associated lattices can be scaled in such a way that they contain one inside the other with index P, okay? And so this is a familiar thing. It's a homogeneous tree of valency P+1, and it has a natural action of the group PGL2QP, since PGL2QP acts on the homotopy classes of lattices in a natural way, and it preserves the incidence relation between vertices. Okay, and in fact, it acts transitively on the set of vertices and edges of this tree. Okay, so the use of this tree is that it actually can be viewed as a universal covering space for this isogeny graph. Namely, if I trivialize the P-adic Tate module of a supersingular elliptic curve and characteristic L, then I can identify, I get an action of the endomorphism algebra of these supersingular elliptic curves. And in fact, I get an identification of the isogeny graph as a quotient of this Brouatitz tree by the action of a certain discrete subgroup gamma. And this gamma is identified with the group of norm 1 elements in a maximal Z of 1 over P order in some definite quaternion algebra. So I take simply a maximal order. There are finitely many such maximal orders up to conjugation in the quaternion algebra. But when I invert P, one can show that there's actually a unique up to conjugation such group. So this group gamma is actually well defined up to conjugation. And this quaternion algebra is the one which is ramified at L and infinity. So it's the algebra that arises as the endomorphism algebra of the supersingular elliptic curve and characteristic L. Okay, so once we've made this identification by fixing this trivialization of the P-adic tape module, we get an obvious isomorphism between the module of harmonic functions on the isogeny graph and the module of gamma invariant harmonic functions on the Brouatid's tree, so functions on the edges, etc. Okay, so we're going to be exploring that a little bit later. Now I want to talk a little bit about further geometric structures that we can associate to this Brouatid's tree and eventually to this to its quotient by this discrete group. Namely, we're going to consider the Drinfeld P-adic upper half plane, which as a set can be defined as a complement of the projective line over QP inside the projective line over CP. And it can also be viewed as a rigid analytic space. So it can be viewed as the CP points of such a rigid analytic space. And I'll now say a few words about the rigid analytic structure. So how I define a nice notion of functions on this P-adic symmetric space. So essentially, if I have a point Z on the projective line over CP, I can write it in projective coordinates in such a way that the two coordinates Z1 and Z2 are integers in the ring of integers of CP and are relatively prime to each other. So that's what this prime means here, that the two coordinates generate the maximal idea, I mean, the full ring of integers of CP. And now I'm going to define HP greater than epsilon to be the set of Z's for which this difference, AZ1 minus BZ2, this is the P-adic absolute value, is greater than epsilon for all pairs AB and ZP squared prime. So what this amounts to doing is where this is a kind of this difference here is a kind of a distance of the point from the boundary, which is this P1 QP that I've deleted. So if I take points which are at distance epsilon away from this boundary, then I get a subset which is properly contained in the P-adic upper half plane. And one can write the upper half plane as an increasing union of these regions, HP greater than epsilon, as epsilon ranges over all positive real numbers. And we say that a function is rigid analytic if its restriction to all these subsets, these HP greater than epsilon, can be expressed as a uniform limit of rational functions having poles outside of this region. Okay, so that's our definition. And it turns out that this notion of rigid analytic function has a lot of the nice formal properties that we're used to expect from complex analytic functions on the upper half plane. There's notably the principle of analytic continuation holds for this class of functions. So I'm going to say now a little bit more about these regions and what they look like. And I'm going to begin by a misleading picture of this HP greater than epsilon. So you might think of it as a P-adic counterpart of the usual Siegel domains that one encounters when studying the complex upper half plane. So if you visualize the P1 of QP as the analog of the real line and HP as the analog of the upper half plane, although it's really two copies in some sense, then this HP greater than epsilon can be imagined as this set of points that are at some distance epsilon away from the boundary. But in the Archimedean setting, this region has a very poor topology. It's a contractible set, and so. And the real line itself is a rather simple thing. But in the P-adic world, the projective line over QP is really kind of a very complicated thing. It's some kind of Cantor set. And we'll see that these regions, HP greater than epsilon, have a more and more complicated topology as epsilon approaches the boundary, so to speak. And that's the topic of my next slide. So if I look at the region, for example, HP greater than 1, if you think about it, you'll realize that it's just a complement in the projective line over CP of P+1 mod P residue disks, where I've excised from the projective line over CP a collection of P+1 residue disks about the P+1 points in P1 of FP. And in doing so, of course, I've removed all of P1 QP and a lot more, of course, as well. And that's what this region looks like when epsilon is equal to 1. But as you approach, so if you look at the region HP greater than 1 over P, you get a complement of P times P plus 1 smaller residue disks. These are now mod P squared residue disks, if you want, centered at the QP rational points of P1. And so on and so forth. Okay, so at if you take now epsilon to be 1 over P to the n, so getting smaller and smaller in an Archimedean sense, then this region is a complement of a larger and larger number, P to the n times P plus 1 in this case, a number of residue disks with smaller and smaller p-adic radii. Okay. And so here's a picture. I mean, for the HP greater than 1, we can think of it. So it's I've drawn the picture for P equals 2. We can visualize it as a kind of p-adic tubular neighborhood of a little piece of the Brouattis tree for P equals 2. Okay, so here are the 3 residue disks that have been removed. And we see that these 3 disks are in somehow natural bijection with these 3 edges of the Brouattis tree. And when P equals 2, we get this somewhat more complicated picture. And for general case, you can imagine sort of this Brouattis tree as being a tubular neighborhood of the entire tree, and the domain for epsilon equals 1 over P to the n is just this sort of the tubular neighborhood of the region of the tree, which is the set of vertices which are at distance at most n from a given fixed central vertex of the tree. So that's maybe a more accurate way of actually picturing the p-adic upper half plane and these kind of Siegel domains that I've introduced. Okay, now we can talk about rigid analytic modular forms. Once we have a p-adic symmetric domain, which plays the role of the upper half plane, well, we say that a rigid analytic modular form of weight 2 on this group gamma, on this discrete group gamma, is simply a function on H, which transforms like a modular form of weight 2. Okay, so that's the definition. And well, the usual yoga, something transforms like this, then it's a section of a certain line bundle, which is identified with the differentials on, in this case, on the p-adic upper half plane, which are gamma invariant. So it actually descends to a differential on this quotient. And I'm going to denote by S2 of HP mod gamma the space of weight 2 modular forms on gamma, which is identified with the gamma invariant differentials on HP, or equivalently the differentials on the quotient of this, on this rigid analytic curve, which is the quotient of HP by this discrete group gamma. And the key fact, which I'm going to be using now, sort of that I want to introduce, is that there's a natural residue map which associates to any differential on HP mod gamma a harmonic function on the edges of the Brouattis tree, which is gamma invariant. And going back to this, I'm not going to say too much about how this is defined, but I mean, it's very simple. Going back to this picture, if we have a differential on HP, we can look at its restriction to these Siegel-like domains and then calculate their residues. Now, this differential is just a limit, a uniform limit of rational functions, where all the poles are concentrated on these removed disks. So for every disk, we can look at the sum, if you want, of the residues and then take the limits. And that gives us a number for every disk, which we then ascribe to the corresponding edge on the tree. And the residue theorem implies that this resulting function on the edges of the tree satisfies the property of being harmonic, that the sum of on all the edges coming out of the given vertex is 0. And of course, the gamma invariance is a consequence of the fact that the original F is a gamma invariant differential, given that the residue behaves in a perfectly compatible way, in a perfectly equivariant way relative to this action of gamma. Okay, so we can now, one of the ideas that I learned also when I was a graduate student, which quite fascinated, which captivated me, was the fact that this residue map has an explicit inverse, which sends the gamma invariant harmonic functions on the tree to the space of differentials. So one can actually define this And this is I call the Schneider-Teitelbaum transform. I first encountered it in a wonderful paper of Jeremy Teitelbaum. And maybe I should say a few words about that, because I started my lecture by saying how influential the paper of Mazur, Swinnerton-Dyer has been in the subject. And this paper of Teitelbaum was sort of grew out of his earlier work with Mazur and Tate on a P-adic analog of the Birchon-Swinnerton-Dyer conjecture for the Mazur-Swinnerton-Dyer P-adic L function. And this paper itself was inspired, or grew out of this work of Mazur, Swinnerton-Dyer. So I think a lot of this paper was really very seminal and led to a lot of different things. Okay, so I was talking about this residue map, and what's wonderful about it is that it takes something which seems very simple on the face of it, just a function on a finite collection of edges of a finite graph. And out of that, it reconstitutes the entire rigid analytic modular form attached to this function, to this harmonic function. Okay. And there's even a multiplicative refinement of this Schneider-Teitelbaum transform, which lifts the logarithmic derivative. So if you have the group, so here A star is the group of non-vanishing rigid analytic functions on the P-adic upper half plane. And I have a natural map from A star modulo multiplicative scalars to the group of differentials, sending F to dF over F if you want. And this multiplicative Schneider-Teitelbaum transform lifts the logarithmic derivative. So it fits into this commutative diagram. It's only defined on harmonic functions with integer values. So you need to have this kind of integrality. But that's the kind of thing that might be satisfied with if you have a Hecke eigenfunction with rational systems of Hecke eigenvalues. Okay, so we have this kind of nice refinement of this Schneider-Teitelbaum lift. Okay, now I want to talk a little bit about the rigid analytic functions which arise naturally in the setting of, if we were, say, to be interested in studying the Birchon-Swinnerton-Dyer conjecture, for example, for elliptic curves of conductor LP. So if E is such an elliptic curve, then I can consider the associated Hecke eigenfunction in the space of harmonic functions, gamma invariant harmonic functions on the Brouatist tree. I'm going to call that kappa. And then the theory of Cherenek-Drinfeld tells us that if I take the multiplicative Schneider-Teitelbaum transform of this harmonic function, then I get a function which is well defined up to scalars and invariant under the action of the group gamma. But actually, the scalars that arise in the transformation property are actually, one can be more precise about them. One picks up in the transformation rule powers of the Tate period, giving rise to the P-adic uniformization of the elliptic curve that I started with. Now, this elliptic curve has conductor LP, therefore it has multiplicative reduction at P, and when we study its analytic theory at P, one has this nice invariant, the Tate period. Okay, and that means that this function f sub e can be viewed as a function on the gamma orbits in HP, the quotient of HP by gamma, to the multiplicative group CP star modulo powers of Q. And that rigid analytic quotient is just the CP points on the elliptic curve. And this gives us a concrete way of getting at the rigid analytic modular parametrization of this elliptic curve. Okay. Okay, so that's kind of the story. And to summarize what I've said so far, I've tried to introduce the idea that one can compute modular forms of weight 2 and level n in several different ways. One could examine the Hecke action on the space of gamma naught of n invariant modular symbols, say with z values, or on the space of gamma invariant harmonic functions on the Brouatist tree. And this second approach is a little bit more restricted. Now it applies to elliptic curves whose conductor is a product of 2 primes. But it has a certain geometric richness to it. Namely, out of this harmonic function, one can actually reconstitute an interesting object, an interesting invariant of the curve, of the elliptic curve, namely some rigid analytic modular parametrization, which goes from the quotient of the upper half plane by a certain discrete arithmetic p-arithmetic group to the set of CP points of the elliptic curve. And that's done in a very concrete computational way by applying to this eigenfunction kappa this multiplicative Schneider-Teitelbaum transform, which I alluded to in my earlier slides. Okay, so now what I want to do is explain that one can try to actually combine these two approaches to make a kind of synthesis of them. And this discussion I'm going to introduce now is actually going to apply to the class of elliptic curves which are of prime conductor. So I'm going to focus on that as being the simplest special case of the general construction that I want to describe now. So I'll let E be an elliptic curve of conductor P, and I will now let gamma be the so-called Ihara modular group, the group of 2 by 2 matrices with entries in Z of 1 over P and determinant 1. Now, unlike the p-arithmetic groups I introduced before, which were subgroups of definite quaternion algebras, this is now a subgroup of an indefinite quaternion algebra, and so it's much larger. And in particular, it acts in a less pleasant way on the p-adic upper half plane. It acts non-discretely with orbits that are dense in the rigid analytic topology. In particular, there are no interesting functions on HP, no interesting rigid analytic functions, which are actually invariant under this very large group, the gamma. Nonetheless, I'd like to try to construct something like a kind of p-adic uniformization of the elliptic curve out of the data of the action of this group gamma on the p-adic upper half plane. That's kind of the goal. And so I'm going to let E0 be what I'll call the standard edge of the Brouattis tree. Now, this is simply the one whose stabilizer in the group gamma is the Hecke congruence group of level P. So if you study the action of gamma on the vertices and edges, you'll see that the stabilizer of a typical edge is conjugate in gamma to SL2Z, and the stabilizer of a typical edge is conjugate in gamma to gamma naught of P, and there's a unique edge whose stabilizer is exactly this group, and that's the standard edge that I'm going to fix from now on. And I want to remind you, of course, of the thing I started with, the modular symbol, which was attached to my elliptic curve of conductor P, which is now in the group of gamma naught of P invariant Z-valued modular symbols. There were two of them, what Barry in his lecture alluded to as the even and odd, or the plus and minus modular symbols. And I'm going to, well, I'll try to say something about both of them, I guess. Now, actually, I'm just going to fix one of them. It could be either the plus or the minus, and I'll call that one I sub E. Okay, so what I want to do now is attempt a kind of a synthesis of these approaches based on modular symbols and harmonic functions on the Brouattis tree, and attach some kind of hybrid object to this elliptic curve. And so this is, the synthesis is done in this very simple proposition, which asserts that there's a unique function defined on the product of the edges of the tree times the set of pairs, ordered pairs of points on P1 of Q, taking values in Z, which satisfies the following three axioms, following three conditions. The first is that this function should be invariant under the action of the Ihara group. So if I translate an edge and a pair of endpoints simultaneously by an element in this group, I should get the same value. So it's a gamma invariance condition. The second is that kappa E should be a harmonic function on the tree when viewed as a function in the first variable with the two other variables fixed. And it should be a modular symbol in the second two variables when the first is fixed. Okay, so it's kind of a simultaneously a harmonic function and a modular symbol. And finally, the third condition, which kind of pins it down completely, is that one should recover the original modular symbol I sub ERS by when restricting to the singleton consisting of that single edge E0, whose stabilizer is gamma naught of P. Now, it's an extremely easy kind of formal exercise, just using the properties of the action of the Ihara group on the Brouattis tree to see that such a function exists and is uniquely determined by these three conditions. The main point is that the group gamma acts transitively on the set of unordered edges of the Broussard tree, of the unordered edges of this tree TP. And therefore, this condition 3, combined with the gamma equivariance, determines the function uniquely. And then once one has that function, it's very easy to see, but by its very definition, that it satisfies the property of being harmonic in the first variable and a modular symbol in the second pair of variables. Okay, so what can we do now with this hybrid object? Well, it's very tempting to then try to apply this geometric enrichment that arises from the Schneider-Teitelbaum transform. And what we're going to do then is we're going to obtain a modular symbol with values in A star mod CP star by applying this transform to this function kappa ERS. Okay, so in other words, J sub ERS is going to be the multiplicative Schneider-Teitelbaum transform of kappa E dash RS, where R and S are fixed, and the edge of the thing variable is varying. Okay, now this function inherits the property of being a modular symbol from the input object that we fed into the Schneider-Teitelbaum transform. And so this J sub E is really a modular symbol with values in the group of the multiplicative group of analytic functions, which is gamma invariant up to multiplicative scalars because of this the scalar ambiguity, which is inherent in the logarithmic derivative and this inverse given by Schneider-Teitelbaum. So this J sub E is what we call the rigid analytic modular symbol attached to the elliptic curve E of conductor P. And maybe the first inkling that this object has a kind of rich connection with the original, maybe the geometry of the original elliptic curve. Well, first we can say that we can note that this modular symbol JE is completely determined by a single rigid analytic function, which I'll call, I'll call it phi sub E of E, so phi sub E of Z. Now, I just get this by evaluating J sub E at the pair of endpoints 0, infinity. Now, it might seem like a big loss of information to pass from a general pair RS to 0, infinity, but in fact, the additivity property of the modular symbol combined with essentially the Euclidean algorithm for the GCD, or the theory of Farey sequences, which I'll talk about in a few slides, tells us that we can recover the general JERS just from the knowledge of this one in a very simple way. Okay, so this object is what we call the rigid analytic period function attached to E. So it's a kind of analytic function on the P-adic upper half plane, which really captures a lot of information about the original elliptic curve. Or really, it's really determined by this modular symbol, which was attached to E. And I'll mention, though, that it's not gamma invariant. I mean, it's going to turn out to be, so it satisfies a complicated collection of transformation relations. For example, phi E of Z times phi E of minus 1 over Z is a scalar. Phi E of Z over 1 minus Z times phi E of Z minus 1. So there's a kind of a 3-term relation, a 2-term relation, which for those who are familiar with modular symbols kind of echoes the familiar 2- and 3-term relations in the calculation of modular symbols. And there's also a property of being invariant under multiplication by P squared, which corresponds to the diagonal matrix P 1 over P with zeros off the diagonal. And then there are a bunch of other relations. So this doesn't determine them completely, but it's sort of some of the functional relations that you get for this rigid analytic period function. Now, maybe the first indication that there's some tight geometric connection between the original elliptic curve and this rigid analytic period function is the fact that when we ask for the scalar that determines the transformation rule relating phi E of Z with phi E of P squared Z, now this function phi E is only defined up to multiplication by a scalar, but the ratio phi E of P squared Z over phi E of Z is a well-defined invariant. And when one looks at this ratio, one recovers a quantity which is commensurable with the Tate period of the elliptic curve over QP. So one recovers this Tate period, and the proof of that theorem follows from the proof by Greenberg-Stevens, is really a formal consequence of the proof of the exceptional zero conjecture of Maser-Tate-Teitelbaum, which was proved by Greenberg-Stevens in another paper, which was extremely influential. But again, note the ancestry, so to speak. This work of Greenberg-Stevens grew out of the work of Maser-Tate-Teitelbaum, which itself was strongly influenced by this earlier work of Maser and Swinnerton-Dyer. Okay. Now, as a corollary, I mentioned maybe one suggestive way of reformulating this theorem is the statement that this J sub E, the modular symbol with values in A star mod scalars, actually lifts to a modular symbol with values in A star modulo powers of this scalar, which is closely related to the Tate period, and which is gamma invariant. So one can resolve a little bit of the scalar ambiguity. It's only the Tate period which enters into this ambiguity. And here in this remark, I do remind you that this function is very far from being invariant, even up to scalars under the action of this gamma. It just has this invariance under p squared. But nonetheless, one sees this Tate period now arising in this way. Okay. So the question that emerges naturally when one sees this is whether one can nonetheless extract some kind of modular parametrization from this J sub E. Okay. And really the main interest of this invariant lies in its relevance to the construction of points on the elliptic curve, which seem to be quite new, which go beyond the usual framework of Heegner points, if one wants. And so these are based on the notion of RM points. So a point tau in the p-adic upper half plane is called a real multiplication point if it satisfies the following two equivalent properties. The first is that it generates over Q a real quadratic field. And the second is that the stabilizer of this point for the action of the Ihara group is an infinite group. So if you take any point on the upper half plane, you'll see that very often the stabilizer is trivial. And the only exception comes when the tau in question generates a real quadratic field. And then this matrix which stabilizes it is, the stabilizer is then essentially of rank 1. And so the stabilizer with gamma tau. And a generator of this group is what's often called the automorph of tau. It's a matrix whose eigenvalues essentially are the fundamental unit in the associated real quadratic field. Okay, so that's what I'm going to call little gamma sub tau. Okay, so now we can talk about the RM values of rigid analytic modular symbols. There's a notion of evaluating such a gadget on an RM point. And this simply arises from the observation that there's a natural evaluation map going from the group of analytic functions on the upper half plane, mod Q modulo powers of P, to CP star modulo powers of P. And this map is just the evaluation at a tau in the p-adic upper half plane. Now, modular symbols themselves are intimately connected with cohomology. Namely, if we have a modular symbol, we can construct a so-called parabolic cohomology class by associating to by fixing a base point on P1 of Q and associating to every element gamma the value of the modular symbol on the path, so to speak, from this base point to its translate under gamma. Okay, so having then made this translation to the point of view of cohomology, we can consider the map from the H1 of gamma with values in A star mod Q to the Z to the cohomology with values in CP star mod Q to the Z, which is induced by this evaluation. But the evaluation is not equivariant for the full action of gamma, only for the action of the stabilizer of gamma. So you only get a map to the cohomology of the stabilizer group with values in this p-adic torus. And if gamma tau equals 1, of course, is not a very interesting map. The target is trivial. But if gamma tau is non-trivial, namely it's isomorphic to Z, then the target is essentially isomorphic to CP star mod Q to the Z. So that leads to this following definition. We define the value of our rigid analytic modular symbol JE at the RM point tau to be obtained by taking any base point R in P1 of Q and looking at the value of the modular symbol from R to gamma tau R. That gives us some kind of not completely well-defined modular rigid analytic function on HP, but the upshot is that the value of this modular function on tau is a well-defined invariant, which doesn't depend on the choice of base point R, and is a sort of a well-defined element of Cp star mod q to the z. But Cp star mod q to the z is just essentially the Cp points of our elliptic curve. So this quantity is what we call the value of J at the Rm point tau, and it gives us, therefore, a kind of modular parameterization from the quotient of the set of all Rm points on HP, taken modulo the action of the Ihara group, and taking values in the Cp points of the elliptic curve. And the key conjecture about this modular parameterization is that all these values have are global points, not just p-adic points. Namely, to be more precise, we can see that the stabilizer of tau in the ring of 2 by 2 matrices with entries in Z of 1 over P is a certain order, or rather a subring which is free of rank 2 as a Z of 1 over P module. So that's what we call a Z of 1 over P order in the real quadratic field generated by tau. And global class field theory identifies the so-called narrow class group of this order with the Galois group of a certain abelian extension of the associated real quadratic field F. And so this H tau, which depends on tau via this dependency on O tau, is called the narrow ring class fields of F associated to tau. Okay. And a conjecture, or rather old conjecture by now, formulated around 2000, is that for all tau in the p-adic upper half plane, for all Rm points, the value of this rigid analytic modular symbol attached to E at the Rm point tau is a global point in E of H tau. And so this kind of opens the prospect of extending the theory of Heegner points and so on to the setting of abelian extensions of real quadratic fields. So since this is a memorial for Swinnerton-Dyer, I thought I would talk about the aspect of this conjecture which pleases me the most by far, which is the fact that it lends itself to explicit numerical verifications. So there are very good algorithms, which I'll talk about after this shortly, that allow us to compute these Rm values. So for example, if I take the elliptic curve of conductor 11, which also appeared in Barry's lecture, whose equation is given here, then I can take a real quadratic field at random, like q square root 101. It turns out that this one has class number 1. And I can evaluate the value of the rigid analytic modular symbol. Here I take the one associated to the plus modular symbol and evaluated this Rm point, 1 plus square root of 101, which turns out to be it actually belongs to the 11-adic upper half plane. So 11 is inert, in fact, in this real quadratic field. And then I get some value, which is of the form x over t squared y over t cubed, where the quantities x, y, and t are given here. So when we compute this modulo 11 to the 200, you get a lot of accuracy, and then you can run this through one of the rational recognition algorithms on Paris, in my case, which is based on the LLL algorithm, and which instantaneously proposes these values for x, y, and t. But then you can turn around and plug them back into the original equation for the elliptic curve and verify that, lo and behold, they really do satisfy that equation. So they really are genuine global points defined over this real quadratic field. So that's actually convincing evidence, of course, for the conjecture, as well as giving a rather good and efficient method. Now, I chose this one a little bit on purpose because it's a real quadratic field which happens to have a Mordell-Weil generator of rather large height. So it gives an impressive looking example, so to speak. There is a second numerical example involving the elliptic curve of conductor 37, which is the smallest elliptic curve of analytic and algebraic rank 1. Okay, so here I've taken a real quadratic field which has large class number. This one has class number 11 and relatively small discriminant for such a class number. And here one can compute the value of the corresponding rigid analytic plus cocycle on this Rm point, and one gets a pair xy where the coordinate x appears to satisfy this polynomial of degree 11 with relatively small coefficients. And here it was only necessary to compute it modulo 37 to the 50 to get the rational recognition of Paris to propose this rather appetizing polynomial. And this polynomial is indeed quite nice because it turns out that it generates, its roots generate the Hilbert class field of q square root 1297. And moreover, when one then replaces xy by the corresponding global quantities, one does get Mordell-Weil generators of this elliptic curve of connector 37 over that Hilbert class field. Okay, so I want to conclude my lecture by talking a little bit about the computational aspects of these rigid analytic period functions and the corresponding rigid analytic modular symbols. So the problem is, how do we represent such a beast, this rigid analytic modular symbol on a computer in a way that would allow us to systematically evaluate it on a large collection of Rm points. So the first proposition which is useful in this is that if the prime P, which is fixed for us because we fixed an elliptic curve connector P, if that prime P is inert in the real quadratic field generated by tau, then this Rm value can be computed using only the restriction of this modular symbol to this basic aphanoid HP greater than 1, which I introduced earlier in my lecture. So this aphanoid, which is relatively simple topologically, since it's the complement of P+1 residue disks in the projective line over CP. And the proof of this is just that if we take tau and we look at its orbit under the Ihara group gamma, that orbit always intersects the basic aphanoid non-trivially. And because the value, the Rm value, is invariant under gamma, so it doesn't change if I replace tau by one of its gamma translates, then I might as well assume that tau belongs to this HP greater than 1. Otherwise, just translate it into that region by replacing it by a suitable translate. So that's kind of nice, because when you look at the calculation of Heegner points using the action of the modular group on the upper half plane, it's sometimes hard to stay within. One always tries, when I'm doing these numerical evaluations, to be as far as possible from the boundary of the upper half plane, where the Fourier expansion converges more and more slowly as you get closer to the boundary. And so here we can stay a uniform distance away from the boundary, no matter what Rm point we take, no matter how big the discriminant is. That's a very useful basic fact. Now, the second useful fact is that if I want to compute this JE of tau to an accuracy of p to the minus m, then it's enough to understand the restriction of the basic rigid meromorphic or rigid analytic period function phi sub e to the basic aphanoid to this accuracy. So you don't need to know the values of this JE at various RS, just at the pair 0 infinity. And this is another very simple proposition. The basic idea goes back to the modular symbol algorithms, which I learned about first in this paper of Maser and Swinnerton-Dyer when I was a graduate student. So here's the proof. If I take a tau in HP greater than 1, then I can write JE of tau as, by definition, this is the value of JE at the pair consisting of the cusp infinity and its value under the automorph gamma tau evaluated at tau. But now this path from infinity to gamma tau infinity, I can subdivide it into a collection, JE R0 R1, R1 R2, etc., up to Rn minus 1 Rn, where these Ri's are chosen in such a way that R0 is infinity, Rn is gamma tau infinity, but the entire sequence, R0 up to Rn, forms what's called a Farey sequence. And a Farey sequence is simply a sequence of rational numbers where if you take the numerators of the successive differences expressed in lowest terms, then that numerator is always plus or minus 1. And the nice thing about consecutive rational numbers in a Farey sequence is that they're all SL2Z equivalent to the pair 0 infinity. That's pretty obvious. Okay, so in other words, I get out of this Fourier sequence a collection of n elements of SL2Z, gamma 0 up to gamma n minus 1. And now I can rewrite this product here. I can write it as a, the typical term is JE of Ri plus 1 of Z, but Ri plus 1 is gamma I of 0 infinity, or gamma I inverse, I guess, of 0 infinity. And then by the gamma equivariance, I can pass this gamma into the argument. And so I get JE of 0 infinity of gamma 0 tau times JE of 0 infinity of gamma 1 tau, etc., up to gamma n minus 1 of tau. And now, of course, this is just nothing else than the value of the rational period function, phi sub e, sampled on these translates of tau under these various matrices. Okay, and the key point why this algorithm works nicely is that SL2Z preserves this basic aphanoid. This aphanoid is far from being preserved in the full action of the Ihara group, but under SL2Z it is. So it also helps us that there's a rather rich subgroup of the Ihara group, which stabilizes this kind of region, this kind of Siegel domain, so to speak. Okay, and now, once we have that, now we can think about how would you actually store in a computer a rigid analytic period function if you desire to have systematically to know its values with an accuracy of some p to the minus m. And this rigid analytic function can be expressed as a certain number of contributions. So here I've been a bit more general on this slide than I had to be. I'm talking also about meromorphic functions. It doesn't really matter for what I'm saying here. So really what we need is a power series for each t in P1 of Fp. These correspond to the centers, so to speak, of the residue disks that I've deleted to define HP greater than 1. And for each of these centers, I give myself some kind of power series in some variable, which is the inverse of z minus this center. Okay. And these coefficients are pretty much free, except that they have to tend to 0 p-adically. So essentially, by storing in your computer a collection of p+1 powers, or even p power series with m Taylor coefficients, each with an accuracy of p to the mod p to the m, so p to the minus m, you get a data structure which is sufficient to capture your rigid analytic period function. Okay, so that's the upshot of this. And then finally, you could ask, well, how do you actually compute this? And now there's a marvelous idea which goes back to a paper of Stevens and Pollack, which allows us to compute these this rigid analytic period function. The key point is that computing this period function is essentially the same thing as calculating to high accuracy the major Swinnerton-Dyer P-adic L function that was constructed in this early paper with Swinnerton-Dyer. And so by exploiting this approach of Pollack and Stevens, we're led to a polynomial time algorithm for computing this rigid analytic period function to an accuracy of p to the minus m. Now, polynomial time here means polynomial in p, in the prime p, which is fixed for us, and the exponent m. So this is a situation which is quite common in p-adic algorithms, where if p was large, this would be a rather bad algorithm, because it's exponential in log p, which is the natural measure of the size of the problem. But if p is small but m is large, then this is actually quite good. So for example, it took us about 20 minutes with a not super optimized algorithm to calculate the rigid analytic period function attached to the elliptic curve of conductor 11 to an accuracy of 211 adic digits. And then once we have that object, which we store in the computer once and for all, and doesn't take much space, so it can be stored on a small, on a floppy disk, if I want to date myself. And then once we have that object, we can calculate the RM values for arbitrary discriminants in a fraction of a second. Okay, and then there's been a lot of software developed for computing these rigid analytic period functions. So with Robert Pollack in Magma, we implemented something which incorporated these ideas on rigid analytic modular symbols, or over-convergent modular symbols of Stevens. As far as I know, this program is now obsolete. The last time I tried using it, I was told that my version of Magma was, that the program was not going to run on the newer versions of Magma. But Xavier Guitart and Mark Masdeo in Sage have implemented a much more powerful, more general, and I think more efficient version of these programs, which also work for quaternion algebras and other things. And there are also various, maybe on a more theoretical level, there are various theoretical analogs of these rigid analytic modular symbols. For example, one could replace gamma by congruence groups, arithmetic groups of a quaternion algebra, subgroups of the Bianchi group, and replacing also analytic by meromorphic functions. And in the latter setting, I should say that for Bianchi groups, there were some nice programs developed by Mac Trifkovich. And for meromorphic analogs, there have been some lovely programs written by Jan Vonk, and that are part of an ongoing project with him. So yeah, this has been implemented in Magma by Vonk. Okay, so now let me just summarize, because I see I'm quickly running out of time. So what I try to convey in this lecture is that modular symbols carry a rich arithmetic information. They allow the efficient calculation of spaces of modular forms. They're the basis for the definition and the calculation of the major Swinnerton-Dyer P-adic L function, as described for the first time in this important paper on the arithmetic of Weil curves. And they lead to the construction of these rigid analytic modular symbols, which then lead to a kind of novel sort of modular parametrization of elliptic curves by Rm points. And this touches on the theme of constructing algebraic points on elliptic curves, which is surely one of the most fundamental questions that one encounters when trying to think about the Swinnerton-Dyer conjecture. And I think I was strongly affected by reading about these questions first in this paper of Mazur and Swinnerton-Dyer. So I wanted to take the chance to maybe thank Swinnerton-Dyer, I guess posthumously, for this important influence. And I'll conclude here, and thank you for your attention.
So, thank you very much, Henri. Now we've got quarter of an hour, a little slightly less, for questions. So please start throwing them.
So I have a question, Henri. In your example, the real multiplication point in the case where the class number was 11 generated that class field, right? And do you expect that you'll get every such, yeah, that example. Do you expect to get every class field of a real quadratic field as generated by some collection of real multiplication points?
I would say yes, except that, I mean, of course, if one fixes a P, then there's a local constraint on the real quadratic field. The prime P has to be either inert or ramified. So for each prime P, one gets roughly half, one gets a theory for roughly half the real quadratic fields. Now, yeah, once one fixes a prime P, then there's always the possibility, I mean, what we strongly believe, also based on data, is that these points behave in all key respects exactly like Heegner points attached to class fields of imaginary quadratic fields. So there are scenarios, conceivably, where there could be torsion. And precisely when the L functions sort of have higher order zeros than one expects normally. And so, yeah, so there should be some kind of Gross-Zagier formula for those. And I guess those questions are a bit subtle. But if one fixed a real quadratic field, one also has the luxury of being able to vary both the prime P and the elliptic curve that underlies the construction.
Yeah.
And so certainly I would expect that in practice, although it would be hard to say something definite in theory, one could systematically construct all the class fields by looking at the coordinates of these so-called Stark-Hagener points. So that's one thing. Now, another aspect of the answer is that one could try to look for constructions that are a little bit less maybe subtle theoretically by trying to mimic, instead of generalizing Hagener points, we could try to generalize different singular moduli, for example, or differences of singular moduli, which are values of modular functions, genuine modular functions of weight 0 on H mod SL2Z, for example. And there one could hope to get a much better control. And that's the kind of thing that I've been studying more recently with Jan Vonk, where we've formulated a notion of singular moduli for real quadratic fields and written down precise conjectures about the factorizations of these algebraic numbers, which are modeled on what was observed by Gross and Zagier in their precursor to the study of heights of Hagener points. And so these singular moduli for real quadratic fields, because we can first thing, we have enough theoretical superstructure to actually prove in significant cases the algebraicity of these invariants, and also establish their factorizations. And therefore, we can actually predict in advance when these invariants will be non-trivial and generate the predicted class fields. So that's maybe a little bit of an easier way of getting at the construction of class fields.
Thank you.
Further questions?
Okay, can I just ask something related to what you just mentioned with sort of analogs to Gross-Zagier? So do you have examples of what happens when the L function has a higher order 0? Do you know that these points?
Yeah, I've done a few computations like that, including some 5,077 P-adic calculations with the curve of rank 3. And yeah, of course, in all the cases where the L functions had a high order 0, sure enough, the corresponding Stark-Hagener points vanished. I haven't been able to check many examples with higher order characters than 2, and that connects to the phenomena that Barry spoke about in his lecture, that the higher order vanishing for non-quadratic characters, non-quadratic ring class characters in this setting, seems to be extremely rare and extremely hard to find in the kind of small, relatively small examples that we can. But we very much believe, of course, that that this would be the case.
So are there more questions? If there's no more questions, perhaps I can just make one small comment on what Henri said about the history, that I couldn't agree more that the discoveries of Birch and Swinnerton-Dyer really reminded the world about the importance of numerical calculations. But I stress it's reminded the world because, of course, there had been this explosion of abstract methods in after World War II. But if you look back in history, I think it was, of course, Gauss computed large numbers of examples of class numbers of imaginary quadratic fields. And I don't think he conjectured it, but certainly someone by about 1820 had conjectured this formula that we now know for the actual, this beautiful formula, closed formula for the class number of an imaginary quadratic field. And it was discovered purely like Birch-Swinnerton-Dyer by numerical calculations. And of course, the great achievement of Dirichlet was to then prove it using L functions. And one last comment is that, as Vey pointed out, I think it's Eisenstein had begun to ask the same question about the L function at s equals 1 of of at least one elliptic curve with complex multiplication. But unfortunately, the computations were not possible at that time, and so he stopped. But I think we should say they reminded the world of the importance of computations, yes.
What's impressive is that these were done in the time when we had punch cards, right? And these programs that they were actually written.
Yeah,
of course, you say that Gauss was doing it by hand, but
right. So, are there any more questions? Then I think we have a 5-minute break until Sarah will start at 4:30 sharp. Thank you.